Okay, so we're looking at some trig identities here. Things to keep in mind with trig identities is, first off, is what we're saying here is that the left-hand side is exactly the same as the right-hand side for any values that are in the domain of these functions here, in the domain of the left-hand side and the right-hand side. So this is an identity. It's always true, provided that it's something in its domain, as opposed to if you have something like a linear equation. This is only true for one value, but this is true for all values, provided it's in its domain. And our goal is to make sure that both sides of this identity are the same. So we want to verify this proof of this trig identity here. It's not a well-known one, so therefore we need to do some algebra techniques, provided we do correct algebra techniques, and we can show that the two sides are the same. Some techniques to keep in mind is you want to always work on one side of the equation or the other. You can't work on both. By that I mean you can't multiply both sides of the equation by something. You can't cross multiply, which really wouldn't apply to this problem here. You can't add or subtract something from both sides of the equal sign. So you always need to just stay on one side. What we'll do is I might just rewrite this right-hand side. In this case, I think everybody knows that secant's 1 over cosine, but I might just change that a little bit. But I'll never do something to both sides of the equal sign. And change everything into sines and cosines is helpful. Multiplying or distributing in this case is helpful. Common denominators is huge, and just good algebra techniques. So let's this one here, the easiest way is probably to change everything in sines and cosines and then multiply by sine. So I get this sine of theta So now I'm going to distribute this sine, so I get the sine of theta times the cosine of theta over the sine of theta plus sine squared theta over cosine theta. So that's just multiplying this sine by both of those. These two cancel, so I get the cosine of theta plus sine squared theta over cosine theta. So now I need a common denominator between these two, so I'm going to multiply this one by cos theta over cos theta. So I get cosine squared theta all over cosine theta plus sine squared theta over cosine theta. I can add these two since I have a common denominator, so I get cosine squared theta plus sine squared theta all over cosine theta. And that's your Pythagorean identity, so I get 1 over cosine theta. And you could just make a little note to yourself, but just don't let me see that you did this, that secant is 1 over cosine, so therefore I have these two being the same, so I can just write down at the bottom that this is true. So this is really the only way that you can change both sides. You can just make a little note as to, maybe I can rewrite this in terms of sines and cosines. It'll make this work easier over here. So that's legal, but usually you erase it so your teacher can't see it. I'm going to do this one two different ways. First thing I'm going to do is just by multiplying these two. Since they're conjugates, there won't be a middle term. So I get the cosecant squared theta minus 1 equals cotangent squared theta. And this is a Pythagorean identity. The identity being cotangent squared theta plus 1 equals cosecant squared theta. So if you just notice that if I just move this 1 over, I have a Pythagorean identity, so therefore I'm done. So you could make a little note on the side over here and say, oh, okay, I know this is true, so therefore this has to be true as well. But you don't want to add 1 to both sides. That would be illegal. Second way we can do is to change everything to sines and cosines. So I'm just going to rewrite these problems with sines and cosines, so hold on. So I just rewrote the cosecant as 1 over sine. I'm now going to multiply. Again, I won't have a middle term, so I have 1 over sine squared theta minus 1 equals. So the left-hand side, I need a common denominator, so let me get a different color. So I'm going to make this sine squared theta over sine squared theta. So now I have 1 minus sine squared theta all over sine squared theta. And this is cosine squared theta over sine squared theta. So again, you can make just a mental note. Cotangent squared is cosine squared theta over sine squared theta. Oh, those two are the same, so now this is the same as cotangent squared. Again, erase this so nobody knows you did that, and then you're perfectly fine. Okay, so here's another one where it's more complicated on the left-hand side as opposed to 1. I can't do anything to 1, so I'm going to work on the left-hand side. I'm going to change everything to sines and cosines and then multiply, and hopefully something nice happens. So this is 1 minus cosine squared theta, 1 plus cosine squared theta over sine squared theta. So now let's multiply these two. I get 1 plus cosine squared theta over sine squared theta minus cosine squared theta plus, oops, that's a minus, what is that? Cos to the fourth over sine squared theta. So we have a common denominator here, common denominator here. If we had a sine squared here, that would be helpful, and a sine squared over here, that would be helpful. So let's just get a little common denominator. So I'm going to multiply this one by sine squared theta over sine squared theta, and change this one into sine squared theta and sine squared theta. So let's just rewrite our problem here. So we get the sine of squared theta plus cosine squared theta minus cosine squared theta sine squared theta minus cosine to the fourth theta all over sine squared theta. Sine squared plus cosine squared is equal to 1. So I get 1 minus, now I'm going to take out a common factor here of negative cosine squared. So negative cosine squared theta, and this is equal to sine squared plus cosine squared all over sine squared theta. And this is not 1 minus cosine squared theta because this cosine squared is married to this sine squared plus cosine squared. Forgot a theta there. Sine squared plus cosine squared is equal to 1. So that's 1 minus cosine squared theta times 1 all over sine squared theta. And let me just slide the paper down a little bit here. 1 minus cosine squared is sine squared theta over sine squared theta, which is equal to 1, which is what our goal was up here. 1. There it is. To me, this one has a lot of secants and tans, so I'm just going to make a little note over here that tan squared theta plus 1 is equal to secant squared theta. Hopefully that'll be handy at some point. It looks like this is the more complicated side as opposed to this one, so I'm going to take out a tan squared theta and have it be tan squared theta plus 1. Tan squared theta plus 1 is equal to secant squared, so that's tan squared theta secant squared theta. And now let's just move some sines and cosines here. So here we go, sine squared theta over cosine squared theta, and this is 1 over cosine squared theta is equal to, so now we just have sine squared theta all over cosine to the fourth theta. Note that I have two terms here, secant to the fourth and secant squared. Well, there's secant to the fourth right here. So I need to have two terms. So how can I make this top one be two terms? I'm going to make that be 1 minus cosine squared theta over cosine to the fourth theta. Well, here's a little side note here. 3/5 plus 10/5 is equal to 3 plus 10 over 5, which is equal to 13 over 5. So everybody's really good at working at fractions and going this way. But if I have this expression here, a binomial or any number of terms in the numerator over a one denominator, just a single term denominator, monomial, I can break it up into two fractions like that. So I can break this up into 1 over cosine to the fourth theta minus cosine squared theta over cosine to the fourth theta. Let me slide the paper down. So this is secant to the fourth theta minus, this is 1 over cosine squared theta, which is secant to the fourth theta minus secant squared theta, and I think that was what we were looking for. There it is. So we did it. Thank you.